Hello everyone, we're discussing semiconductors and so far we have developed p-type semiconductors. Now let's discuss n-type. So this is your silicon crystal. In this silicon crystal, if we add an impurity which is pentavalent, for example phosphorus, so when you add phosphorus in it, phosphorus has 5 electrons in its outer shell. If we add a pentavalent impurity phosphorus in this pure silicon crystal, then what it does, it will replace, let's say, this silicon atom, and once it replaces, it looks like this. This is the impurity and it has 5 electrons. These 4, they are already participating in covalent bonds, but you have a 5th extra electron. Just to highlight this, I have increased the size of it. So this is the extra 5th electron. Remember, this silicon crystal has equal number of holes, equal number of electrons, free electrons. It is neutral. Now what we have done, we have added a pentavalent impurity. And once we add this pentavalent impurity, it provides this extra electron. This extra electron, after gaining energy from any incoming photon, moves into the conduction band. This electron goes out and becomes a free electron and is now present in the conduction band. Once this electron moves out, remaining phosphorus now becomes a positive immovable ion. It's a fixed ion now, it cannot move. We have not created any additional charge. This is positive, this is negative. But this positive ion is fixed, immovable, it is not going to move at all. It has provided us a free electron which is present in conduction band. All these free electrons, they are already in conduction band, and therefore now number of free electron, this increases. There are more free electrons than holes. Because of this, we say that majority charge carriers are negative, and therefore it is called N-type semiconductor. You have an excess of electrons, excess of negative charge carriers, thus giving us N-type semiconductor. Draw this figure and then we'll write a few statements. Write down the statement. When in an intrinsic semiconductor, that is pure semiconductor crystal, a pentavalent impurity is doped, inserted, for example phosphorus, then it has 5 electrons in its valence shell. It has 5 electrons in its valence shell. Out of these 5, 4 electrons participate in covalent bonds with neighboring silicon atoms. Fifth extra electron has an energy which is slightly below the conduction band, and therefore can easily move at room temperature into the conduction band. It just needs 0.01 electron volt types of energy, and therefore at room temperature this much thermal energy is already available. So what it does, it accepts that energy and then moves to the conduction band, leaving behind a fixed positive phosphorus ion, but the process has created extra free electrons, of course, in the conduction band, and therefore there is an excess of negative charge carriers, and therefore there is an excess of negative charge carriers, which is why this type of extrinsic semiconductor, once you have doped, it's no longer intrinsic, it becomes what? Extrinsic. Which is why this type of extrinsic semiconductor is called N-type semiconductor. It's called N-type semiconductor. As a note mention that the whole crystal is still electrically neutral. The whole crystal is still electrically neutral. Let's say there were 3 holes and 3 electrons initially when it was a pure intrinsic silicon crystal. Now when you replaced one of the silicon atom with the impurity phosphorus, it becomes positive, giving us an additional electron. Net charge is still 0, but since this is not going to participate in the current, we say that there is an excess of negative charge carriers. There is no excess negative charge, there is an excess of negative charge carriers. So the whole crystal is still electrically neutral. So we can also draw energy band diagram in this form. This is your valence band. This is your conduction band. And now with this phosphorus added, you get donor energy band, which is closer to the conduction band. This is due to the donor. The phosphorus is in p-type, which we discussed in the previous lecture. Aluminum was acceptor type impurity. This phosphorus is donor type impurity. So it is releasing an electron. This electron is not participating in covalent bond. Its energy is way higher than the energy of valence band electrons. It is closer to what? Conduction band. When we drew this thing for aluminum p-type, this energy band was closer to valence band, which we did in the previous lecture. Draw that figure. Now let's talk about p-n junction. Let's say you have placed a p-type and n-type semiconductor side by side. Although that's not how you form a p-n junction, but for simplicity, what we are doing, this is p-type and this is n-type. In reality, we take a single crystal and from the left side we dope it with aluminum. From the right side we dope it with phosphorus and it becomes what? p-n junction. But for the sake of argument, just say that you place two p and n-type semiconductors side by side. And the p-type there is an axis of holes. Holes are positive. In N type, there is an axis of electrons. So when you do this, it's obvious that since there are more holes on this side, they will try to diffuse from this to this, from left to right. So diffusion of holes takes place in this direction. Hole moves from this side to this side. Similarly, there is an axis of electrons. They try to move from this side to this side. This is diffusion of electrons. When this diffusion takes place, remember, initially this side is neutral, this side is also neutral. But these holes, they found that there is a deficiency of holes on this side. They get thermal energy at room temperature and then they move from P side to N side. Similarly, due to thermal energy, these free electrons, they start moving from N side to P side. When you do this, when you move negative charge into something which is neutral, then this P side becomes what? Negative, and N side, because of the diffusion of holes, becomes what? Positive. So after some time you will find that P is no longer neutral but is in fact negative. N is no longer neutral but is what? Positive. What this does, you may think that this process will continue forever and you can transfer all the holes from this side to this side, or all those holes which find suitable path along this side, and they will move here and recombine. Recombine means a hole and electron will neutralize each other, but that doesn't happen. It's just like capacitors, if you remember. As you are moving these holes, this side is becoming positive. So let's say first hole moves, it becomes 1 positive. Second hole, when it moves, it will be repelled by the positive charge. But say it has more energy, sufficient energy, it can move to this side. Now this side becomes 2 positive. When third hole tries to move, it has to overcome 2 positive charge. So eventually a time will come that the incoming hole will be repelled by the already positively charged N side. At that time, further diffusion stops. And when this further diffusion stops, we say that there is a barrier present at the junction, and this barrier is opposing flow of charge carriers. This barrier is called potential barrier. And this potential barrier is because of depletion layer. At the junction, something called depletion layer develops. Now, what is this depletion layer? Let's understand this. This PN part, let's redraw the whole thing in this form. P side, N side. Now for P side, you've got aluminum fixed ion, which is negative, fixed ions. On the N side, you've got phosphorus fixed ion. Now, when you have two separate P and N crystals, there are electrons, there are holes present. Over here, majority holes, less number of electrons they are present, but system is what? Neutral initially when they are not yet connected. Now when this hole moves from this side to this side, so when I say this side to this side, remember it is basically moving from this place closer to the junction. So this hole H plus now moves from this position to this position. So as it moves, right now look at the region, this is neutral, but the moment this hole moves over here, it recombines with this electron, recombines with this electron or with some other thing, then immediately at this place there is an excess of negative ions. We have depleted charge carriers in this region, and now you have negative ion present, negative charge present. Same thing happens with electrons. So initially you have an electron over here in the conduction band, free electron. This part is electrically neutral. The moment this electron moves to this side, this region is what? Positively charged. Look here. So once this electron has moved, we say that we have created a depletion layer. Charge carriers in this region near the junction boundary, that number of charge carriers decreases, they deplete, and therefore this is called depletion layer. So in the depletion layer, charges are present, but which type of charge? Fixed ion, fixed ion. They are not charge carriers. They are only what? Fixed charges. So in depletion layer, there is a shortage of charge carriers, and it is called therefore depletion layer. And because of this positive and negative charge, you will get what? An electric field. Everybody knows direction of electric field is from positive to negative. This electric field will create what? A potential difference. In the direction of electric field, potential decreases. So this V is high and this V is low. The potential difference is what? Your potential barrier. This electric field is going to oppose further diffusion of holes. Holes are positively charged. They will be repelled or pushed in this direction. They are trying to move over here, but the electric field is going to push them in this direction. Therefore, after a certain time, no further diffusion is going to take place. Are you comfortable with the origin of depletion layer, potential barrier, direction of electric field? absence of charge carriers, there is no absence of charge. Charge is present, but that is in the fixed form. Are you comfortable with all these things? Yes or no? Write down this fast in the comment box and then we'll write few statements. Write down the statement. When p-type and n-type semiconductors when p-type and n-type semiconductors are placed side by side, then near the junction majority holes from p side diffuse into the n side. Similarly, majority electrons from n side diffuse into the p side. Leaving behind immovable fixed ions near the junction. Due to this movement, p side becomes negatively charged. And n side becomes positively charged. This produces an electric field. From N to P, from N side to P side. Remember, just for namesake, we are saying N to P. Direction of electric field is always from positive to negative, which it is in this case also. So which develops an electric field from N side to P side. This electric field creates a potential difference. Near the junction boundary, which is called potential barrier. Because of the electric field, further diffusion of holes and electrons stops. further diffusion of electrons and holes stops. Look at this part also. This is the electric field, and let's talk about the potential barrier. So potential barrier looks like this. Delta V. Potential is same, increases, again remains same. Over here, this side is negative, low potential. This side is positive, high potential. You're moving in this direction, opposite to electric field. When you move opposite to electric field, potential increases. And then this part is electrically neutral, let's say whole thing, this portion. And therefore potential remains what? Same. Similarly, the rest of the crystal on the left side remains electrically neutral. So this figure is giving us the idea of potential barrier. So what we have drawn is a graph of V versus X. V versus X. Note down this. Write down PN junction in forward bias. What is forward bias? This is your PN junction at equilibrium. And now if we connect an external battery, so when you connect this external battery, what it does, this terminal is positive, this terminal is negative. Let's concentrate on majority charge carriers. You can understand everything for minority charge carriers also with the same logic, but in the opposite direction. This hole is not able to cross over to this region. Why? Because this side is positively charged, hole is also positively charged. So further diffusion stops. Now, let's talk about it has some energy of 10 joules. Let's talk about in joules for easy understanding. It has 10 joules of energy, and to overcome this barrier, it needs 11 joules. It cannot get additional 1 joule at room temperature. There is not sufficient energy in photons which they can deliver to this hole. So its diffusion has stopped. But Once you connect this positive terminal, its positive potential is going to repel this hole, or you can say this positive terminal now can give it that extra 1 joule of energy. The moment it gets that extra 1 joule of energy, it starts again moving in this direction. Same thing happens over here. This side is negative, this terminal is negative. This electron doesn't have sufficient energy to move to this side because this negative charge is repelling it. Depletion layer developed because of movement of these charges only. But now further movement has stopped. They don't have enough of energy. That extra demand of energy is being fulfilled by the negative potential, negative side. This negative side is going to repel the electron so that it can overcome repulsion of this negative charge, and this electron moves in this direction. These two will not cancel each other. This is the movement of holes, positive charge. This is the movement of electrons, negative charge. Overall, in this direction, we have developed what? An electric current. This electric current or this movement of holes, it does what? It decreases width of depletion layer. It decreases that potential barrier, and because of that decrease in potential barrier, your current increases. If you draw a graph of I and V, so as I increase the voltage, this I starts increasing and then it increases abruptly. What it does, what it shows you, as you are increasing V, as you are increasing this positive potential, this hole gains enough of energy to move and cross to the other side. But as I further increase the potential, almost all of the holes can move. That increases the current. But at the very beginning, only those holes which had powerful energies, let's say 9 joule, 10 joule, 8 joules. There are holes which have only got say 1 joule, 2 joule. So this positive potential, if you provide energy through the positive potential to a hole which only has 1 joule of energy, then it cannot overcome the barrier because it has to have 10 joules or 11 joules of energy. Only those which are near about that 10 joule mark, 8 joule, 9 joule, 10 joule, they can easily get energy from the positive terminal of the battery and move to the other side. But as I keep on increasing this potential, as I keep on pushing the holes from this side, almost all the holes can move, and similarly all the electrons can move, thus increasing overall current. So this slow growth which you see, this is roughly 0.7 volts for silicon. At near about 0.7 volts, that potential barrier which we had, the potential barrier which I showed you, that potential difference is of 0.7 volts. So if you can overcome that 0.7 volts, you find that a current is present in the circuit. Draw a figure and then we'll write a few statements. Write down the statement. when a PN junction is connected in forward bias, when a PN junction is connected in forward bias, holes in P region which could not move to N region because of the potential barrier at the junction gain sufficient energy to do so, to move into that N region. Similarly, majority charge carriers, free electrons in N region now have sufficient energy inside the bracket because of the negative terminal of the battery. Because of the negative terminal of the battery, and therefore can move and enter into the P region. Both these movements develop a current from P to N which increases as we increase voltage of the battery, which increases as we increase voltage of the battery. Now, remember, I had told you that photons are coming, they are creating electrons and holes. So that thermal process is a function of temperature. It has nothing to do with voltage. So this process continues at all times. Photons are coming, they are breaking bonds, creating electron and hole pair. Those electron and hole pair, they are moving in this direction, they are cancelling each other, but this extra voltage has now given enough energy to the holes on this side and electrons on this side, to the majority charge carriers, thus giving us an overall current I shown in the graph. Remember, the flat portion slightly going up, it tells us that as we are increasing voltage, depletion layer, its width is decreasing, that is potential barrier is decreasing. So write down this. As we increase the voltage, width of depletion layer decreases, that is potential barrier also decreases. That is potential barrier also decreases. So let's say initially it was like this. If initially it was of this type, now it will look like this. Increase the voltage. Increase the voltage. So this potential barrier keeps on decreasing. Note down this much and then we'll discuss reverse bias. Let's talk about PN junction in reverse bias. So this is your PN junction and we have connected the battery with reverse polarity. Now what happens? Forget the battery now for the time being. This hole, once potential barrier develops, cannot move from P to N side. It is being repelled. It finds difficult to overcome repulsion of the positive side, which is the N side. Now what you have done, you have made this terminal negative. So whatever tendency or willingness it had to move to this side, that is being further decreased. This negative terminal says, instead of moving that way, come to this side. That means no diffusion now can take place, no movement of majority charge carriers can take place from P to N. Similarly, this side is positive, this side is positive. This electron wants to go and diffuse to this side, is being repelled by the negative charge present at the potential, present at the depletion layer at the junction boundary, but this electron is now being pulled in this direction by the positive terminal of the battery. So its further movement towards this side becomes even more difficult, even more restricted. That means in this condition, current flowing in the circuit will become what? Zero. This is what PN junction is good for. Stopping current in this direction in reverse mode. It can allow current only in one direction, that is in the forward direction. In reverse, current becomes what? Zero. So it behaves as a valve. Flow can take place only in one direction. Flow cannot take place in the other direction. So if I change the voltage like this, I can increase the current or I can drop it to zero, creating a situation like 1 or 0. That's what the whole thing is all about. Creating a setup where you can stop or start flow of current by simply changing voltage. Now, when we plot a graph of I and V in reverse, then it is found that, well, you all saw this part. In this, it was in the forward region and the scale was in milliampere. If I use reverse polarity, that will be kind of using voltage in the negative region. Reverse polarity means voltage is what? Negative. And the special thing is, this side current will be written in microampere. At one point, we'll discuss this point, look is almost same, but range is different. This is milli, this is micro. At a particular voltage, let's call it V0, abruptly current increases, and what this abrupt increases and what this whole thing micro and milli is, let's understand this also. In forward, current is because of what? Majority charge carriers. Majority means more current, current in milliampere range. But just look at the whole structure. This is whole. When I have a battery like this is going to support these, giving us what? Current in milli. But instead of this, if I have a battery like this, then it is going to support what? This minority charge carriers. Minority charge carriers will be now favored by the positive terminal. They are trying to diffuse. They are trying to diffuse from this side to this side. H is being attracted by the negative side and gets an additional push. So this current is small because we are dealing with basically what? Minority charge carriers, and therefore current is in micro 10 to the power minus 6 region. What about this particular voltage? This is called Zener region. What this Zener region does, forget about this battery now. This was just to explain that flow wise you must get same behavior this side or this side. This and this, they are same. The difference is in the numbers. Majority, minor, majority, minor, majority, minor. Now, as I increase the voltage in reverse direction, these holes, they start moving in this direction, but they are minority charge carriers, and therefore we don't see any great change in the value of current. Current almost remains zero. If it's in micro region, you can say practically it's almost what? Zero. But after a certain voltage, what happens? This positive potential is so high now that it breaks these silicon covalent bonds. You don't need any incoming photon. This positive potential is so high that it can easily break this covalent bond, and once it breaks the covalent bond, it creates what? A hole and a free electron. That hole becomes what? Part of the minority charge carriers. Now you can understand as if it is now becoming majority charge carriers. So what it does, This high potential breaks what? A covalent bond, producing an electron. That electron will be repelled by this. You are increasing plus, you are also increasing what? Minus. So this plus and minus, high voltage the battery has broken the bond, created a hole and an electron. Hole and electrons, they are moving in this direction and in this direction, developing a current in this direction, which is in the macro region. But as you keep on increasing the voltage, more number of bonds break. And as more number of bonds break, there is an increased supply of holes and electrons. This increased supply, what it does, let's talk about holes or let's talk about electrons. As these electrons are available and when they move, they collide with other bonds. These moving electrons, they now collide with other electrons. They now break the bonds. Apart from this, the colliding electrons now are breaking what? Bonds. And when they break bonds, you further create what? Additional electrons. So there is an avalanche of electrons. It's just like avalanche of ice. So there is an avalanche of electrons, and that avalanche of electron and holes creates what? An abrupt increase in current. So now when you try to increase the voltage, it doesn't increase and only increases what? Supply of charge carriers. That means beyond a particular voltage in reverse direction, you cannot increase the voltage because electrons, voltage means what? A kind of resistance. But these electrons are no longer able to oppose anything. They are basically creating more charge carriers themselves. That is called avalanche current, and that avalanche current takes place in what? Zener region. And this zener region is something which is important for us. Why? If I design a device where I need constant voltage, for example, you have a stabilizer and that stabilizer is CVT, constant voltage terminal. So what that constant voltage terminal tells you that even if voltage increases, overall voltage which is being used by the electrical device should remain constant. In that device, if I use a Zener diode works in this region. So even if voltage increases, external voltage increases, voltage across the Zener region in the Zener diode is not going to increase. The thing which is going to increase is what? Current. This Zener part we'll further discuss in the next class. I hope you have understood at least the working part of Zener region. If you have understood a little bit of this reverse bias and Zener region, then write down yours in the comment box and then you can leave. Thank you very much.